More than 80 years ago, two complex cells united and became a single, unique cell, the beginning of new life. This cell divided and redivided to form trillions of specialized cells that are the cooperative community known as the human body. This body has lived through billions of experiences, each carefully filed in a control center of unbelievable complexity and capacity, the human brain. Each second, this brain receives, analyzes, sorts, and files hundreds of millions of bits of information and issues the millions of orders required to keep the body alive and functioning. This brain, working through this body, will share some of its accumulated wisdom with you today. Welcome, Dr. Paul Brand.
Last time I was here, or the time before, I told you really the background of these series of discussions and talks, lectures. It's very important that each of us, as we grow up, should have a sense that we are wonderful, that we are remarkable scientific products, and that we are made, we are designed to be very special. Whether you're a winner or a loser, you're still a remarkable person, and composed of a whole collection and variety of things that are way out wonderful. Scientists today have been trying to reproduce. I personally, I told you last time, I personally was responsible for a big research program in the United States to try to reproduce the sense of pain for people who couldn't feel pain. And I've also been associated with programs to put the hand, all the mechanical features of the hand, onto a computer, then into a book. And my engineers and the others who work with me are just, their mind boggles when they see how much precision and coordination there is in the hand or in any part of the body. And the reason I want to emphasize this is that today biologists are still talking about evolution by chance. Now, obviously, there's evolution in the sense that there's a whole gradation in different types of animals, and that the higher animals have features that the lower animals don't have, and yet they have many features in common, which shows either that you have a common designer. It's like an evolution of automobiles. The people who make a Rolls-Royce or a Mercedes have picked up ideas from Ford and others in the earlier stages, and so you see features all the way up. But there's design. There's design. I think it's mathematicians more than anybody who is saying that these things just couldn't have happened by chance. No matter how many mutations occur, it's too precise. And so that's really the focus of what I'm trying to say, to emphasize design. And remember that in classical biology teaching at the school level today, we're still saying, people are still saying, that all the things that happen in the body, the development of the tongue and the eye and the hands and the feet, all happened by chance, mutation, and the survival of the fittest. Now today I'm talking about the eye. We had the hand before, and then we had pain. And I don't, this guy's looking at you now, but my eye is better than that. This is a bit crooked. I want to put you into the position as if you were a designer. Supposing I said to you, now, there's a whole race of people that we've discovered living on some island, and they're just like anybody else. They're wonderful people, but they don't have eyes. They can't see, they can hear. And we have been given the task of developing a system whereby they could see. We may have to start with babies and embryos, but we've got to put something in there which, how many problems would you have to face? In how many areas would you have to be very precise and know a lot about different sciences in order to create an eye and connect it with the brain and tell the brain what to do to be able to see? I can see all of you, and I imagine most of you can see me. But actually, no light from me is entering your brain. It's simply an electronic imaging, and I'm really just in your imagination. How does that happen? How does it work out? I've only got a few minutes to talk about it, but I want to leave you with that sense of wonder. Now, there are 7. I've defined 7 things that have to be worked out and designed and coordinated in order to make it possible for a brain to see the images of what's in front. Let me just run over them. First of all, light. You've got to arrange for light to go into the body. Most light stops at the skin. It doesn't get through. There's no light inside my hand. There's no light inside my skull. But light has got to get into the body, into an eye. Secondly, there's got to be an optical department. There's the optical department over there. All you guys have got to figure out how to turn just light into an image that can be transmitted to the brain. Then, after you've figured out how to make an image of light, you've then got to have a system that we call in engineering a transducer system. A transducer is when you take one type of image and turn it into a totally different medium. For example, when a television camera looks at a person, the camera sees light, and the camera turns it into electronic signals, which are transmitted to the television receiver, and the television receiver turns electronic signals back into light, which you can then see. Now, what I'm going to ask you to think about is how, when you receive light into your body, you turn it into electronic signals that go through into the dark, dark brain, and they don't take light into the brain, they take signals which the brain then turns back into an image. Not a light image, but a visual image. And then the brain has then got to take hold of that visual image, make it into a kind of a 3D situation, see all the movement, and connect it to memory. So that if you see somebody whom you've seen before, you meet them in the corridor, you say, aha, that's so-and-so. And it reminds you of all the things you've done together and the last conversation and the questions you asked each other. That is the thing that makes it meaningful. You remember their name, you remember their history. Now, let's take those one by one, and you just think to yourselves, what does it take to do that? Okay, now the first one, light has got to get into the body. Now, the entire body has to be covered with skin. There's no part of your body which doesn't have a membrane equivalent to skin covering it. And there are many reasons for that. Skin is tough. If I want to work with instruments, if I want to tear a branch from a tree and it's rough, I don't want to destroy the delicate cells inside my hand. And therefore, it's important that the whole of the body is covered with something tough. Now, that's beautifully done. I'm not going to spend time on it, but the cells of the surface of the hand and the surface of the face are formed first in what we call a germinal layer. That means that it's a living, dividing layer of cells all over the body. And they aren't transparent. I mean, they wouldn't let light through, but they're not very tough. They're alive and active. And they keep dividing, so that when there's a layer of cells here, and they divide, then there are 2 layers. And then the cells here are pushed up and they become 3 layers. And all the division is taking place deep. And the cells are getting closer and closer to what ultimately is going to be the surface of the body, okay? And the cells that are deep down are very delicate, and they have to be kept wet in order to avoid drying and so forth, but that's all right because they're inside the body. And then as they get towards the surface, a new protein is infiltrated into them, a protein called keratin. Keratin is what your fingernails are made of, your hair and your surface of your skin. And as the cells become infiltrated with this tough, hard, opaque material, as the keratin gets towards the surface, the cells get flattened and hardly alive. There's no real activity. They couldn't possibly divide. They couldn't possibly do anything intelligent. But they just get thinner until finally they're just flakes. And ultimately, if you rub your hands together, all sorts of little microscopic flakes will fall off your hand, and they are the dead cells, the keratin cells that have, in moving towards the surface, they become tougher and tougher and less able to live until finally they're thrown off. And that's going on all the time. It's going on very fast with some of you kids, very slowly with me. My metabolism isn't as fast as yours. Now, that is what normally happens, and it's designed that way to protect the body. Even the surface has to be kept a little bit moist, and therefore we have sweat glands coming through the skin and pouring sweat so that your skin, when you feel it, is just a little bit moist, but it isn't wet, except when you get scared. Now, here's our problem. With the body being purposefully covered with keratinized skin, how are you going to punch a hole through it so that light can get in? That's the only question we have to answer. How can I get light into the body through the skin? Well, the obvious answer is you have an eye. And that's the trouble with some biologists, is that they think in terms of yes and no. Am I going to have an eye or am I not going to have an eye? And yes, you need an eye. But in order to have a patch of skin that is transparent, beautifully, clearly transparent, we call it the cornea, in order to have that, you've got to have a whole bunch of scientific disciplines working on it. Now, you can all divide yourselves up into groups if we had time, and I'll tell you some of the things that you have to do. First of all, there's an obvious problem in that anything which is going to be totally transparent cannot have a blood supply, because the blood that flows through blood vessels is opaque. You see a pool of blood, you can't see through it into what's underneath because it's full of cells. It's full of red cells and white cells and different kinds of cells. So if you had blood vessels running through your cornea, you'd be looking through a network of vessels and you'd hardly see anything. It'd all be very dim. And therefore, you've got to have a tissue which will live without blood supply. Now, what does blood supply do? Why is it important that every other part of the body has a blood supply, except your cornea? Maybe some other exception. But anyhow, your cornea doesn't have it. Well, a blood supply carries defenses from infection. Therefore, your cornea has no defense against infection. The blood supply carries moisture to keep the cells covered with water so they don't dry out. And so it defends and it nourishes and it keeps it moist. Now, how are you going to, if you insist upon a transparent skin, transparent covering, how are you going to deal with these things? Well, let's take nourishment first. How can you nourish it without a blood supply? Well, you see here is a diagram of the eye, and there is the cornea, which you have decided to make transparent. It's got no viability of its own. It's got to be wet on the outside to prevent the drying out of that delicate material, and it's got to receive nourishment. Well, there's some things put in here, and you guys who had this research project of how to make a skin transparent, you thought about this. You see, here is a very rich blood supply, and that rich blood supply has a special feature to it, that as the blood vessels have a fairly high pressure of blood, they are designed, the blood vessels are designed to filter out of the blood a clear fluid, not ordinary serum, which is kind of opaque partly, but a clear fluid containing all the nourishment that came in the blood. So all the things that need to sustain the life of a piece of cornea flowing out. And that fluid comes out here underneath it flows out here and it fills part of this, and then it comes out through the pupil and it circulates underneath the cornea. And the cornea has a tiny layer of single transparent cells on the underside, which allows that filtered fluid to be refiltered back into the cornea. And all the nourishment that the cornea needs, all the things it needs to survive, come from the bloodstream, but the bloodstream is way off to the side and doesn't interfere with the... So that's pretty cute, pretty clever. It's a thing that doesn't happen in many parts of the body, but there it is. So well done, you've dealt with that. Then you've got to keep it wet. You've got to keep the outside wet. Doesn't matter about the inside, but the outside will be evaporating because there's no thick skin over it. And that delicate collagen membrane, which has no toughness to it, all the fibers are parallel, that delicate membrane's got to be kept wet. So what do you do? Have you got that? Well, you were doing that, weren't you? What do you do to keep it wet? Well, here you are. Congratulations, this is what you thought out. But it needed some thought. You put a gland in here, and this gland is very much like a salivary gland. You know, your mouth is wet, isn't it? The inside of your mouth. And the mouth is wet because you have glands that secrete a digestive juice into your mouth called saliva in order to help you eat. Well, a very similar gland is put here, but it doesn't secrete digestive juice. It just is largely wetness. Wetness together with a little mucus to make it slippery. And that pours out here somewhere over the cornea. And it's called tears. The fluid that comes out of the lacrimal gland is like tears. And it's wet. But you know, have you ever been driving in a car when it's raining? Or when you've just squirted your windshield wiper fluid and you get a stream of water coming up over the... Does that help you to see? Can you see better? Is the windshield more transparent when there's a stream of water over it? Come on, you're all scientists. It doesn't help, does it? A lot of little droplets and streams here, and part of the windshield may be dry and part of it's wet. It hinders vision. So what do you do when it's raining? That's right, yeah, there you are, that guy's with it. You have windshield wipers. And these wipers simply, they don't take the water away. The windshield is still wet after the windshield wipers have gone, but it spreads the liquid evenly over the windshield. So they're not individual drops and individual streams. It's just a layer of moisture. So it stays wet, but you can see through it because it's transparent and it has no optical, the water has no optical effect. What do we call the windshield wipers in the eye? We call them eyelids. And, you know, the one problem about eyelids, you forget to use them. Well, actually, you don't forget to use them. But why don't you forget to use them? Not because you're intelligent, not because you've thought this out and recognized it and saying to yourself, my goodness, I haven't blinked lately. I better keep my cornea moist. That isn't the way we think about it. We think about it because we are forced to blink. Have you ever tried, stand in front of a mirror and time yourself with a stopwatch, how long you can stay without blinking? Well, anyhow, it's very difficult to stop blinking. You can't do it. And so, in the cornea, there are hundreds and thousands of little tiny nerve endings that give a signal when your cornea is dry. It feels uncomfortable. They're nerves like pain nerves. And you feel uncomfortable and you're forced to blink. You blink because you must, because it's really a pain. It's a pain situation. And all of you, every one of you here are blinking. Look at them. Look at these, they're blinking now. And you're doing it because it's important to do. Not just because a chance thing. It's important and fundamental. It takes pain to do it. Another thing, you know, the cornea can't defend itself against scratches and punches. So the body has thought out, some intelligence has thought out that the eyelids, which have to go across to keep the eye moist, it's made of thick skin, and it has fibrous material, plates in it, and if you see something coming towards you which you think might be damaging, you automatically blink. It's really a fear mechanism, and it means that your eyes are covered over with thick skin at that particular moment. Very helpful. But you know, even so, in a sandstorm or in dusty situations, your cornea could get scratched. And if it got scratched, it would get infected. And if it got infected, it would be destroyed. And every time you had a conjunctivitis, a little pink eye from some infection getting in there, you might, because you see, none of the immune cells of the body can get to the cornea because blood supply isn't there. You had to have it that way in order to make it transparent. So what do we do? Well, the intelligence that designed the eye and the cornea said we can put something into the tears. We can put a material called lysozyme. Lysozyme. And this little gland which makes tears and keeps the eye moist also puts into those tears this protective enzyme which works like an antibiotic and destroys germs that might happen to land on your eye. Okay? That's taken a lot of thought and of planning. One other little thing, it sounds silly to say it, doesn't it? But it's important that the transparent patch in your skin should happen to lie in front of the light-perceptive retina. It's the retina that's going to take the image to the brain. So it's very important that the light perception patch, the cornea, shouldn't be over here or on the tip of your nose, while the rest of the eye is behind intact skin. You know, one of the problems that biologists face is that these things are so obvious when you say them, but they're not obvious in the course of evolution. Evolution happens only by chance. You don't have the patch of skin that's transparent in front of the light perceptive cells because it ought to be that way, but simply because by chance it happens there. And by chance it could happen anywhere. It could happen on your buttocks, transparent skin on your buttocks. And your eye could be pointing up on the top of your head where you wear your hat. In some way it must have been thought out. Do you all know what a neural tube is? Have you studied the chick embryology? Huh? Well, look, this is it. At the very beginning of embryology, and this is taken from a chicken, but it's the same, basically, this part of it is the same in a human. The surface of the embryo is just a layer of cells. And it's like this. There you are, a layer of cells. And then two little bumps arise like this. Two little bumps. And those bumps are the beginning of what is called the neural tube, which becomes the brain and spinal cord. And here, as time goes on, these grow higher and higher and come across. And now you can begin to see that it's almost made a tube. And this tube is made of ectoderm, and my red chalk is ectoderm. And finally, these two meet, and when they've met, the embryo joins up again, and here is the neural tube. And this is going to be the brain and the spinal cord. Now, after that has happened, you begin to get the eye forming. And the eye are these two buds here. And they grow out from the neural tube like this, and they make half a cup. And this is really an extension of the brain. This is on the brain. And all this lining here in the cup is made of light-sensitive transducers, okay? Now, you need to have light to get to that. And therefore, the outside skin here, which is left behind, that is this layer of skin, creates something which is going to be a cornea. And it does that like that, and it makes a cornea. And this is transparent. And these are the eyelids, and here is the transparent cornea. Now, it's very important for the transparent cornea to be in front of this. And gradually this grows down, and this grows up, until they meet the dermal ectoderm and the neuroectoderm, forming two half cups, or two cups. And if you can imagine a little embryo, these two cups approaching each other like spacecraft. You remember when the two spacecraft docked with each other? It took hundreds of scientists to work out how to make a spacecraft from over here meet a spacecraft from over here, and they didn't go past each other, and they didn't just half meet each other. They slowed up, and they backed off, and they slowed up, and finally, everybody in Houston cheered, and they met absolutely perfectly, and they formed one spacecraft. Now, exactly that happens, and has happened in every one of you, when your optic brain cup went up and your skin cup, becoming transparent, moved down and made an eyeball. Beautiful. I've not seen any eyes that have been like this. They all meet in a remarkable way. And it's really quite remarkable. And when they meet, all the stuff here between ectoderm and ectoderm is called mesoderm. And mesoderm makes things like muscles and bones and other structures. And as these two meet, they grab a bit of mesoderm, and that mesoderm is going to form the iris and the ciliary muscles and so forth. So the thing that I want to tell you is that the lower cup, the brain cup, manufactures some kind of complex chemical, I don't even know its name, which infiltrates around it and says to the dermal ectoderm, the skin, says, I need a cornea in front of me. I need a lens in front of me. I'm in the dark. Now, that's all in chemical language, but it determines where the cornea is formed, so that the cornea doesn't just happen in front of the eye, it is asked for by the neural cup. This is all in the dark. It's all in a baby embryo that has never seen the light. It's dark in the uterus, too. And to me, it's amazing. It's absolutely amazing that it should happen and be right every time. Now, second department. We mustn't spend too long on this. Second department is the Department of Optics. Now, you know something about optics, don't you? About refraction through lenses and this kind of thing. Not only has light got to come into the eye to get to the brain, but it's got to be refracted with great precision to make an image. You see, if you look at a piece of white paper, light gets to it, and the light that gets to it is reflected from all your faces. But I can't see your faces there. But if I took a lens and refracted it, I could then get an image, a light image, of what is out in front here. And that is what the optics of the eye does. I'm not an optician, and I'm not going to spend time, but here it is, you see. Here is the eye, here is the cornea, and here is a lens. And that lens is extraordinarily precise, as is the curvature of the cornea. And between them, they bend the light, as in a prism, and they focus it on the back of the eye. And the light that comes from here focuses over here, and the light comes from here focuses over there. I've just, since I last saw you, I think it is, I've had a cataract operation in my eye. My eyes have lasted 79.5 years, and they've been very good. But about 78 years, this lens became a bit clouded, and it said, you've lived too long. And so I outlived my lens, and I went to an ophthalmic surgeon, and he said, well, the best thing was I'm going to take that lens out and put another one in. And you know, he employed 3 optometrist optical specialists because he was not specialized enough, even though he was an eye surgeon. And I sat in a chair on 2 different days while these people brought huge machines to measure exactly the optical characteristics of my lens and the distance from here to here and the distance from here to the back of my eye and the width of the eye. And they figured out finally, as a result of all their careful design, they came up with some numbers, and they said to Dr. Lindquist, who was my surgeon, they said, you need to put a lens into just this place where the previous lens was, and it's going to be just so far from the retina, and therefore it needs to be just so thick and so wide and have a curvature on the dorsal side and a curvature on the underside. And Dr. Lindquist looked through all his catalogs and all his stores of lenses, and he picked out a lens just right for that particular eye. It's this one. Just right for that particular eye. And then when he operated, he made a little hole to the side here through the sclera, and he took out the other lens, and he put this lens into the same capsule, and it worked. It fitted. But you know, supposing while he was pushing it in, he'd been looking over, reading a book or something, that lens might have slipped. And instead of going here, it might have fallen down over there. Or it might have been here. And then it wouldn't have been any good. The image would have been totally blurred and useless. And so I said to him afterwards, I knew him a little bit, I said, you know, you've taken a lot of trouble over placing this, but you know, the biologists tell us that the placement of the lens, along with everything else in the body, just happened by chance. And there's no reasoning behind it. It just happened that way. And if it was a good eye, it survived, and if it was a bad eye, the patient died. And I said, do you feel that you're any better than the God who designed us? And he looked at me and grinned. He said, no. The original eye was just a little better, but I had to try to imitate it. And all I'm going to say to you about that is that there is precision there. You know, a lens formed by chance mutation, not only might not have been a lens, it might have been opaque. Not only did it have to be crystalline, not only did it have to be the right shape, the right thing, but it had to be in exactly the right spot. And I, for the life of me, don't know how one can say that a lens just happened. Because, you know, it isn't difficult I mean, the substance of a lens isn't anything very complex, and you could have made dozens of them. My little embryo, when it was growing, could have put half a dozen lenses in my liver. Or it could have had a lens in my cheek or back of my neck. And the thing is, it wouldn't have done any harm anywhere. Now, this is an important principle I want you to get. To make dozens of lenses, just for the heck of it, and put them in different parts of the body, by chance, which is what one might expect from chance mutation, it wouldn't have done any harm. Of course, if I hadn't had it in the right, providing I had one in the right place, maybe just one eye came in the right place, or nearly in the right place, the others wouldn't do any harm. The fact that there are not any other lenses in my body suggests that it's something more than harm that makes you eliminate lenses. Why is it that there's a lens only in the right place and nothing anywhere else? I can imagine, you see, if in the embryo started making something unnecessary but very big, like an extra bone, and stuck it in my stomach, I mean, that obviously would be harmful. That would be a harmful mutation, and it might hinder my chances of staying alive, and therefore I would die, and my successors wouldn't have it. But if it's something like just a lens, any old where in the body, it's doing no harm, and providing the rest of the body was very good, maybe better than most people's, then why not just leave them there? And it doesn't prevent my surviving. So the survival of the fittest isn't going to eliminate harmless but unnecessary organs all over the body. And yet today we can't find any. And that means that there must have been intentional making and designing of lenses, and intentionally saying that they're not needed anywhere else. Okay, well, I'm going to leave the optical department and move on to the transduction department. Anybody know what a transducer is? We talked about them, I think, 2 lectures ago. A transducer is a little machine, a little device that changes the nature of one signal and makes it into another kind of signal. There are many examples of that in the body, but for example, the street lights. You know, when I was a kid, street lights used to be turned on by a person who was lighting them. And every evening, the street lighter would go around all the lampposts and switch them all on. And they'd stay on for the night. And then, in the morning, when it became light, he would go around all the lampposts again and switch them all off. But then they decided it was going to be cheaper to put transducers in there, light transducers. And these light transducers worked so that as soon as the light came beyond a certain intensity, the transducer turned it into an electric current, and that current switched off the light by itself. And when it became dark, because the night was coming or because you had an eclipse, the transducer said, hey, it's dark, and it made a current which turned the light on. Okay? So the transducer takes light and turns it into something else, like an electric current. And here's your eye. And you've got light coming in, which is great. You've got the light there, but it's just no image. Then you've got the optical system, the curvature of the lens and the shape of the curvature of the cornea and so forth, and that focuses the light. And here on the back of the eye, exactly the right distance from all these curves, you've got images, little actual images, images of your face, images of your green and your blue and your white and all these things. It's all there on the back. And now it has got to be changed, because that light cannot go through your skull into your brain, and if it did get into your brain, it wouldn't mean anything. So you've got to have a whole bunch of transducers. And in the body, we call them rods and cones. And here you can see these are supposed to be, these little bulgy things are called cones, and these long, thin things are called rods. And this is all exposed in the retina to the images. And so if, supposing this little cone here signals green, well then if there's somebody here with a green shirt, and the image of him happens to lie over that cone, it will signal green. And that will be picked up by all these nerves and taken to the back of the eye, where it goes into the optic nerve. And the rods don't tell color, but the rods are very sensitive to low light. And so therefore, there are a lot of rods around the side of the eye, like here. There it's mostly rods, here it's mostly cones. And if you're in the dark, and you're trying to find your way in the dark, and there's a candle way over there, and there's just some dim residue of daylight, and you're trying to find your way, you will find your way without color. The images that you see in the near dark are all just black and white. But they're very, very sensitive, and it's carried by the rods. But when the light comes on, and you can begin to see things clearly, color comes into view, and they're carried mostly by the cones. And each cone has its own color that it transmits. And so the nerve, when it has an electric signal coming from one of the cones, it says, aha, that means there's a green spot just there, and there's a red spot just next to it, and this is beginning to make up into something like a face. Now, this is quite remarkable, and I want you just to realize that there are not many materials that are light sensitive, not many materials that you can use. I think selenium is one, but if you're making a light transducer, you're restricted, very restricted, in the materials which will respond to light and turn it into a current. But the body somehow has collected from the bloodstream, from the liver, from the food you eat, from whatever it is, has collected just materials which are light sensitive, or even green sensitive, or blue sensitive, and has put them into these rods and cones, which happen to lie at the back of the retina, and happen to have images made on them by the optical system, because it's a different group of scientists that have made the optical system from the scientists that made the transducers that pick up the image and turn it into electric current. Now, that electric current in itself is quite remarkable, and I wish I had time to tell you, but basically, the nerve that goes from these rods and cones and picks up the signals and carries it back to the brain, and the nerve that carries it back to the brain are very similar to all the other nerves in the body. And I'm not going to be able to go into detail about nerves, but nerves are not simple wires that take a current, like an electric current from a telephone. The body is too wet to insulate wet nerves carrying an electric current. But there is a remarkable way that it happens, and I'm going to oversimplify it just to give you an idea of what I'm talking about. A nerve is basically a tube. It's a tube of a membrane, submicroscopic membranes running from your fingertips, from your eyes, from your ears, into your brain. And this is a membrane, a semi-permeable membrane, which means that chemical ions can permeate through the membrane. And when you take ordinary salt, here you don't have a complicated chemical, ordinary salt, you take salt, you dissolve it in water, it ionizes, and the sodium atoms, sodium ions are positive electrically, and the chlorine ions are negative electrically. And the unique thing about a nerve is that there are little pumps. I call them pumps I don't have a better word. These little pumps push the negative ions outside the tube and the positive ions inside the tube until finally the tube is just full of positive ions and all around it are negative ions. This is a little bit oversimplified. When you get a stimulus, when something happens that says, it's happened, I'm being touched, I hear a noise, I see a light, whatever it is, that membrane becomes depolarized. And the positive ions escape, and the negative ions get inside. And that wave of depolarization sweeps up the nerve to the brain and tells the brain what's going on. And as soon as it is past a certain area, and you get a mixture of ions inside and outside, this little pump pumps the positive ions back inside again, and the negative ions back outside again, and restores the polarization between the negative and the positive. And a nerve impulse has passed, and it's now ready for a new nerve impulse. And every time you see something, a whole bunch of nerves are changing from positive to negative and negative to positive, and these little pumps are busily restoring the polarity, and it's a wave of depolarization. Now, you don't understand that. In fact, nor do I, to be perfectly honest. We don't understand it, but it's quite amazing, quite extraordinary, that every one of us, every newborn baby, has a system where millions and millions of nerves are being constantly polarized and depolarized, and messages are passing up and down, and they all carry the same sort of message. They all say that the message has happened. Now, what message is different every time? And the brain receives these little beeps, these little signals from polarization and depolarization of the membrane. It receives it the same for sight, and the same for hearing, and the same for touch, and the same for anything else. But the brain knows where that message came from. And if it receives a little message along the nerve that came from a green cone, it says, aha, there was a spot of green over there, and now it's gone. And that sequence of messages, scientifically coordinated, is picked up by these cells, and they become a new image. You create an image in a brain, to the back of the brain, where there is no light, only beeps, and there's never been any light in the brain, never will be, and yet it gives you the clarity that I'm seeing here. And it's just extraordinarily beautiful. You know, here are two eyes, left and right, and here are two nerves going down to the brain. One goes to the left brain, one goes to the right brain, left eye, right eye. You know, that's perfectly satisfactory. You don't need anything different from that. But somehow the designer of the optical system thought, wouldn't it be just a little better if we could have the images from both eyes on the same side of the brain, rather than simply the light from both sides? And they realized that this eye uses this side of the retina to see over there, and this side of the retina to see over there. And this side here sees over there, and this side sees over there. Now, rather than having the images from two eyes on the two sides of the brain, let's take the image from this side of this brain and mix it with the images from this side, from this side of this eye, with this side of that eye, so that all the things you see looking that way and looking that way are the same, and they're different from what you see looking this way and this way. And therefore, somehow, I don't know how it happened, somehow between the embryo and the adult, all the nerves from this side of this eye crossed over here and joined the images seeing from this side of this eye. And so this green is here and here, and this red is from here and here. So that this brain, the left brain, sees both eyes' images of that side, and the other side of the brain leaves both sides of this eye. Isn't that cute? I mean, it isn't necessary. It's just an extra fancy. And how do you uproot those nerves and cross them over and mix them up and bring them out here in two separate nerves? This is called the optic chiasma in front of the pituitary gland. I just think it's a very, very cute little extra that we all have, and it just shouts of design. I could go on for hours talking about this and about the way in which the brain has to connect that image to previous times when it's seen the same image. Once I've seen an image, then it's stored. And when that same image comes up another time, now I recognize that young lady in brown as being here last time. I remember her face and the way her hair comes down. I saw that, not by light, but by a brain three-dimensional image several weeks ago. And now when I see it again, it comes back and, you know, she was there last time. And if it weren't for that, images would mean very little. If every time you saw something, it was the first time you'd ever seen it, it wouldn't be meaningful to you. You wouldn't know what you're thinking about. Anyway, ladies and gentlemen, you are wonderful. You are wonderful. And I want you to realize that you have been designed. Designed for a purpose, that there's thought, intelligence behind. I'm not going to try to tell you who designed it or how it became, but there's design and there's intelligence, and you're worthwhile. So thank you very much for listening.